Hello, today we're going to review Unit 4 for the AP Chemistry exam. It has to do with reactions and stoichiometry. We're going to go over some free response and multiple choice questions. Okay, so we're reacting 0.3 grams of methyl salicylate with a strong base. This product is acidified to produce salicylic acid crystals. And then they said for every 1 mole of methyl salicylate, 1 mole of salicylic acid crystals are produced. Calculate the maximum mass in grams of the salicylic acid that could be produced. So this is a stoichiometry question, 0.300 grams of the C8H8O3. They gave us the molar mass, which was super nice. Always, whenever you see grams, change it to moles. And then they told us that it was a 1-to-1 relationship there. So for every 1 C8H8O3, we make 1 HC7H5O3. And then finally, we need to get that back to grams. So we need to use the molar mass of the salicylic acid, which is 138.12 grams per mole. Moles cancel. The methyl salicylate canceled. So now we just need to calculate. So you would do 0.3 divided by 152.15 times 138.12, and you get, so you did 3 significant digits, 0.272 grams of the salicylic acid. And that one was just 1 point. Okay, so now we're going to purify those salicylic acid crystals, and you're going to filter it from the reaction mixture, rinse with distilled water, and then dry it. And they give you the following table, and we have an 80% yield of the dry salicylic acid. So the students suggest some of them dissolved in distilled water during the rinsing step, as the students claim consistent with the percent yield. So yeah, it is consistent. If you have a percent yield that's lower than the theoretical yield, for some reason there is less salicylic acid being measured on the filter paper. And this makes sense because you can see in the data table there is a very slight solubility in water. So it's possible that some of it dissolved, making the yield lower than expected. And this was just 1 point. Okay, so this one is part C. Calculate the quantity of heat that must be absorbed to increase the temperature. So this is actually a Unit 6 question, but I'm going to go ahead and answer it. I don't feel bad if you decide to skip forward, but just so you know, this is a thermochemistry question. So because we have a mass of the sample, and then we have a temperature change, we can use Q equals MC delta T. And so our mass is 0.105. Our specific heat capacity in joules per gram Celsius is 1.17. And our change in temperature, if we subtract the 159 and the 25 degrees Celsius, that'll give us our change in temperature. So when we calculate, multiply those together, we get that our Q is 16.5 joules. So that is to change the temperature. That one's for the first part there. The second part is and then we have to melt the crystals completely. Right? So we need to use the heat of fusion to find the heat for melting. And that's kilojoules per mole. So what I have to do is change that 0.105 grams to moles first, using the 138.12 grams per mole. Then I can use the heat of fusion, which is 27.1 kilojoules per mole. And that will give me 0.0206 kilojoules, which is equivalent to 20.6 joules. I went ahead and turned it into joules because our Q from the change in temperature was also in joules. They have to be in the same unit. So that way I can add them together and get my total heat for that whole process, which is 37.1 joules. And that one was 2 points. One for getting the individual joules correct and one for getting the total joules correct. So that is how you do that. Okay, for part D for this question, we have methyl salicylate and salicylic acid that give us the structures. It says the same three types of intermolecular forces exist among molecules of each substance, but explain why the melting point of salicylic acid is so much higher than that of methyl salicylate. And the reason has to do with the additional possibility for hydrogen bonding present in salicylic acid. In methyl salicylate, you only have one kind of possibility where the hydrogen can then form a hydrogen bond, but you have two possible areas in salicylic acid. So that's why the salicylic acid melting point is so much higher, because it has those stronger intermolecular forces. And that one was just 1 point. Okay, so here's a different response question. We want to look at the solubility of calcium hydroxide, and it gives us a KSP value. So I know this is going to have some Unit 4 information, but also some Unit 7. But A is definitely a Unit 4, writing a balanced chemical equation, dissolution of calcium hydroxide solid. When it dissolves in water, you're going to break it apart into the ions. Calcium forms a 2+ ion because it's an alkali earth metal, and then the hydroxide ions are -1 charges, and there's 2 of them to cancel out the 2 charge from the calcium ion. So that is a dissolution equation. It's dissolving in water now. B is really a Unit 7 question, so I'm not going to go over that one here, but I wanted to look at the balanced chemical equation and those solubility equations there. Part C for that question is actually a really good one as well to go over. In the box below, complete a particle representation that includes 4 water molecules with proper orientation around the calcium 2+ ion. So, and then they gave you a drawing to emulate. So when you have a water molecule like that, the smaller parts are the hydrogens, and the larger is the oxygen. Now I wrote in the charges, even though they're only going to be partial charges in an actual water molecule, but I wanted to show you that the oxygen is going to have that slightly negative side, and that slightly negative is going to interact with the positive charge from the calcium ion. So really we're drawing ion dipole interactions. So when you draw your 4 water molecules, you want to make sure that the oxygen side is pointing toward the calcium. And that you only have 4 water molecules, you don't draw extra, you don't draw fewer than 4, and then you need to make sure all the oxygens are pointing toward it. And that was 1 point, all or nothing for that particle drawing. Okay, so let's do some multiple choice questions. They give us an equation that we need to balance, and it specifies all coefficients reduced to their lowest whole number terms, which they don't have to specify, but you know, it should always be reduced. The coefficient for O2 is what? So we have this really big compound here. Okay. I'm going to start with carbon. There's 10 carbons on this side, so I can fill in a 10 on the right. 12 hydrogens, but 2 in water, so I can do 6. 6 times 2 is 12. There's 4 oxygens here, but there's also 4 oxygens here and multiple oxygens, so I'm going to ignore that for the moment and save that for last. And then finally, let's look at sulfur, and it looks like there's 1 on the left, so just 1 on the right. Now, go ahead and add up all your oxygens on the product side. There are 20 plus 2 plus 6, so there's 28. On the product side, 28 oxygens, so that means there has to be 28 oxygens on the reactant side, and there are 4 in our large compound. So I have 24 additional oxygens, which I can achieve by using 12 oxygen molecules. So your answer is C there. Okay, I'm sorry this one was a little hard to fit on the slide with those drawings, but it says which one shows the formation of water vapor from hydrogen gas and oxygen gas. So we know that hydrogen gas is diatomic, so H2. We know oxygen gas is O2. And when we're forming water vapor like this, I would have to balance the equation like that. And it said everything was gases, vapors and gases. So if you'll notice, all of the product sides are the same. Okay, I have 6 water molecules. Right. So in order to make 6 water molecules, I would need 3 oxygen molecules, and I would need 6 hydrogen molecules. A doesn't work because the oxygen and hydrogen atoms are separate, same thing with B. C and D, I'm just looking for the correct numbers. So C is the correct answer there because we've got the 3 oxygens, which are larger than the 6 hydrogens. Okay, so this time we've got a titration based on this reaction here. We have 25 milliliters of an acidified iron 2+ solution. Requires 14 milliliters of a standard 0.05 molar permanganate solution to reach equivalence point. Remember, equivalence point is when they completely balance each other out in that reaction. You have no excess of either thing. So for this one, I want to go ahead and take the 14 milliliters. I'm going to change that to liters times the 0.05 molar. That will give me moles of the permanganate solution. And so I get 7 times 10 to the negative 4 moles. And then I can use my mole ratio. That's why they give us the balanced equation. There, for every 1 MnO4, there are 5 of that iron plus 2. So essentially I need to multiply by 5, and I'll get 0.0035 moles of the Fe2+ solution. From there, I can divide by the liters, which is 0.025 liters, to get the molarity, or 0.14 molar for the iron. And there's your final answer. Okay, here's another permanganate reaction. So in this one, we've got permanganate ions and bromide ions and some acidic hydrogens reacting. And we want to track how many electrons are transferred in the reaction represented by the balanced equation above. So this is an example from redox reactions, which you introduce in Unit 4. So the easiest thing to do is to track the oxidation numbers. Now hydrogen here is a +1 because it's a monatomic ion, but in compounds hydrogen is also +1, so that's nice. Oxygen in compounds is -2 unless it's a peroxide, which these are not peroxides. Bromide here is by itself. It's a monatomic ion. It's -1. It's the same as its charge. This bromine is by itself, but there's no charge, so it's 0. This manganese is a +2. It's a monatomic ion, so it's the same as its charge. And then the last one here, I need to use the oxygen to calculate the manganese. So that's a -8, and I want it to add up to -1 overall. So the manganese must be +7 to get that to work. So you're seeing that the manganese ions are going from +7 to +2, and it's doing that twice because of the 2 coefficients. So you'll see that there must be a transfer of 10 electrons because manganese is gaining 5 electrons essentially twice over the course of that reaction. And then balanced equation above. So if you had half reactions, you might have been able to say like 5 for the manganese, but because it's by the balanced overall reaction, we want to say 10 as our final answer. In Unit 4, we also introduced the concept of acids and bases and simple titrations and conjugate pairs. So when you have, when it's asking for a conjugate acid, we know this thing must be a base to begin with, because you'll have a base and then its conjugate pair is a conjugate acid. Bases like to accept hydrogen ions. So it goes from NH2 negative and to NH3, so it always goes up. And it also goes up 1 in charge, so it goes from -1 to 0. So B is our correct answer. So that is for a base and its conjugate acid. Let me give you another example. If I have something like NH4+, and that's acting as an acid, I wanted to find the conjugate base, I would take away a hydrogen, and it would go down in charge. So just be aware of those conjugate pairs and how they work. They're always 1 hydrogen difference, and therefore 1 charge difference. So be careful with that.